Hola a todos, ¿qué tal? Bienvenidos de nuevo al seminario de álgebra. El día de hoy tenemos a un invitado, a Chengyu Wu, quien nos va a hablar sobre on the overlapping strings and their associated SFTs. Thank you very much, Chengyu. It's a pleasure that you have accepted to talk in our seminar, and we are looking forward to your talk. Thank you.
Okay. Thank you for the introduction, and also thank you for the invitation. It's my pleasure to give a talk here to introduce you things we did on the overlap set of strings and the associated SFTs. This is a joint work with my collaborators Nishant Chandgotia and Marcus and Jacob Richey. So here's the outline of things I'm going to talk about today. I'll start with some preliminaries on symbolic dynamics, and then move to the first part of my talk, which is SFTs obtained by forbidding one word indeed in one dimension. Start with some earlier results on the different relations between different quantities of these SFTs, and then introduce the main problem we have, which is when will such two SFTs be conjugate to each other, and introduce our main result and generalizations. And after that, I will move to the higher dimensional case where we don't have that much results, but some things are there. I will briefly introduce that also. Okay. So let me start with some preliminaries on symbolic dynamics. So from symbolic dynamics point of view, so we always start with a finite alphabet, we denote it by A. And the space we consider is the subspace of the so-called full shift. And full shift is basically just a to the power z. They are just bi-infinite sequences over this finite alphabet. And then we have a shift spaces here. Shift space is basically a shift invariant subset of a to the power z. By shift here, I really mean shift map, which shifts the sequence one bit to the left. Usually the shift space can be described by listing all the forbidden word. Well, forbidden word basically means that the word you never seen in the all the points in the shift spaces. So you can list them one by one. They are countably many, so you can list them. And this list of forbidden word we denoted by F. And in that case, we write the shift space as X sub of F. They are just the points contains no words from F. And most of the case, your F will be an infinite set. But in case your F can be chosen to be a finite set to describe the shift space X you have, then we call this as X and shift of finite type. And this is one of the main object in symbolic dynamics. And one simple example, just to give an idea of what it is. So if your alphabet is binary and your forbidden word is just only one word, then that basically means that the things in the corresponding shift spaces is just all the binary words with no 1 occurring. So, and this is a well-known golden mean shift. And the last thing I want to mention is about here is about the presentation of SFTs. So every SFT can be represented by a finite directed graph, where the points or if you like, the elements in the shift space corresponds to bi-infinite paths on the graph. This is a directed graph and it's finite. Okay. And we have some properties of shift spaces people usually consider. So one of them is the so-called irreducible. So irreducible shift space basically means from any word any two word can be connected with another allowed word. And correspondingly on the graph, this basically says if you have a edge on the graph and there's other edge also on the graph, then you can always connect them by a directed path. And since you have a graph, then you can always represent the graph as a adjacency matrix or consider it as a adjacency matrix. Then the irreducibility can also be studied from the adjacency matrix. On the adjacency matrix, it basically means that, well, the matrix is adjacent. Is irreducible. And you have space. Then we have to talk about space. If you have two spaces, then people really consider the map between them. And this map is so the map we always consider is called sliding block code. And using topological from topological point of view, so sliding block codes are just continuous and shift commuting maps between spaces. This is indeed due to Curtis-Harlan-London theorem, I think. So it said that sliding block code are just continuous shift commuting maps. And what are they? So they are indeed maps defined by local rules. A local rules that really means so to define this sliding block code, well, you first you're given a block map, which is fine. Block map which maps here, if on this graph, it maps all the strings of length m plus n plus 1 to a single bit yi. And this local rule of capital phi is given, is fixed. And then if you want to generate the whole image of a sequence X, then you apply this block map at and for each of the block of length m plus n plus 1. You apply it here to generate yi, and if you want to generate yi plus 1, you just shift the window one bit to the right. And then you apply the same map to get the corresponding value for y of I plus 1. You can and then similarly, you shift it again to get other bits, and eventually you generate the image of the point, which is y here. So, yeah, three more definitions of the map. You have map, then when people want to study the properties of the map, we care about when it is onto, when it is one-to-one, when it's when it's a bijection. So when it's one-to-one, we call it embedding. When it's onto, we call it factor code, and when it's one-to-one, we call it conjugacy. And indeed, there's three properties of the sliding block code correspond to three, in my opinion, most important problems in symbolic dynamics. One of them is the embedding problem, and then the factor problem, and also the conjugacy problem. So embedding problem basically means that if you are given two shift space, when can you embed one into another? Can you give a characterization of this? And the factor problem is, well, again, given two shift space x and y, then when can you map one into the other in when can you map it onto the other shift space? When can you construct a factor map between them? And conjugacy problem maybe is the most famous one among them. It's given two shift spaces. When can you get a conjugacy between two shift spaces? And for conjugacy problem, indeed, when the two spaces are both SFT, given x and given the y, then there's a characterization called amalgamation and splitting. There's a characterization, but this characterization basically is not, people don't know whether it is decidable or not. So in terms of this conjugacy problem has been open for more than 50 years. So given two shift spaces, or you can consider them as two matrices, then whether you can build a kind of continuous shift commuting map between them, and whether you can decide whether they are conjugate to each other in finite time, this is something people don't know whether it's decidable or not. So indeed, in this work, we focus very much on these conjugacy problems. Okay. Now let's move to the main target for our work, which is the SFTs obtained by forbidding one word. I start with a one-dimensional case. So let me first introduce the notation here. So we always consider a word W, which is on an interval over the alphabet Q. We always suppose the length of the word is K. And then we denote X sub of W to be the SFT, the shift space obtained by forbidding this word W from the full shift. Here, full shift really means the full Q shift over the whole the whole alphabet. So originally, so the question we originally consider is the following. So if you choose two words, let's make it relatively simple. So if you take a word U, which is 10110, and V equals 10100, and consider the two shift spaces, then which one has larger entropy? Well, here entropy will mean topological entropy. So you have shift spaces, they are sequences, then you have periodic points. Then the entropy you can consider as just the growth rate, the exponential growth rate of periodic points. And for SFTs, there are some easier ways to calculate them, which correspond to SFTs. As I mentioned, you have graph representations. For graphs, you have adjacency matrices. And then for adjacency matrices, you can take the largest eigenvalue, which is always real by the Prunus-Rubinian theory. And then you take the log of the eigenvalue. That turns out to be also the topological entropy of SFT. So you can think either ways. Then the problem is if you're given this word U and V, and then you have the two corresponding SFTs, then can you tell which one has larger entropy? Well, I kind of already tells you the way to approach this question is to look at the adjacency matrix and calculate the largest eigenvalue. But that's kind of complicated because calculating eigenvalues requires some computation at least. Even though this is a small example, you really need to do some work to calculate. So our question is, can you determine it immediately without any computation? Or can you directly, whenever I give you two word out semblance, can you directly tell me which SFT have larger entropy? That's kind of the question we already ask ourselves, and that motivates this whole work. Okay, so if you want, you can make a guess here. So just choose either one which you think have larger entropy and write down your answer, and later I will tell you which one has larger entropy and see whether you make a correct guess or not. Okay, and it turns out that the answer to this, by determining which one has larger entropy without any computation, the answer to this turns out to be related to the overlap of the two words, or overlap. Sometimes we also call it autocorrelation. I will use these two terms interchangeably. So now let me start to introduce what is overlap and how it is related with the entropies and also other quantities of the shift space. So again, we look at word W equals is of length k, so base are W1 to WK. Then the self-overlap set of the word is given by this. So there are all the integers I from 1 to k such that if you look at the word W, you look at a prefix of length I, it is just the same as the suffix of length I. Or one way to visualize this is to think of you have two copies of W. They start at the same position. Then you just translate the word I bit to the right. Then the two words will overlap in on an interval. And if on this interval the letters you see for the two words coincide, then we say that this I is in the overlap set. Basically means that you can restart the word W from its S position, I or I plus 1. But yeah, you can check this. So that's basically how we can visualize this overlap set. And it worth noting, there are two things I want to point out here is, first of all, this overlap set, self-overlap set, let's call it self-overlap set, is always non-empty because the number k is always in the set. If you have a word here and you just put another word downward, you don't translate at all, then it must, they are the same word, so they must coincide. Or in other words, if you the prefix of the word of length k is the same as the suffix of the word of length k, because they are the same thing. That's the first thing. So k is always in this self-overlap set. And the second thing I want to point out is, well, you can use the same idea to define the cross correlation between two words. So if you have one word U and another word, let's say V, then you can use the same idea to define the cross correlation between U and V. You just put a U here, and then you put a V downward, and you just translate one bit to the right and see when on the overlap interval, then the two patterns agree. And you can define overlap set similarly for two words here. But a slight difference between the self-overlap set and the cross correlation set between two words is the self-overlap set here is always, it doesn't really matter if you translate to the left or to the right. They give you the same overlap set. But for two words, U and V, if they're different, then if you translate to the right, you get an overlap set. If you translate to the left, then you may get a different overlap set. Or in other words, the overlap between U and V can be different from the overlap between V and U. And indeed, that's most of the time that's the case. Okay, that's about overlap. And turns out that this overlap is very much related to several other. Well, I mean, this overlap set is not really from symbolic dynamics. It's simple enough. And it turns out that this simple property of the word is related to the SFTs obtained by forbidden one word. It's very much related to the following quantities from symbolic dynamics point of view. So let me briefly introduce them. So the first quantity we will introduce here is a so-called correlation polynomial. Well, as I said, you have an SFT, then you have a graph, you have an adjacency matrix. For the adjacency matrix, you can calculate the characteristic. Sorry. That's the third thing here. Sorry. So the second thing here is a correlation polynomial. That's basically just you encode the information of the overlap of the string into a polynomial. So you have if your I is in the overlap set, then you just have t to the power I minus 1, and you take the sum over all the i's, all the number s in the overlap set. That's correlation polynomial. So correlation polynomial contains the same information as the overlap set. And then you have characteristic polynomial. The characteristic polynomial is, well, you have an SFT, then you have a graph. From the graph, you can build the adjacency matrix. And for the adjacency matrix, you have its characteristic polynomial. And that's what we mean by characteristic polynomial. Here you do have a factor, but this is kind of due to some technical reasons, because SFTs, you can always recode it into a larger, into a higher block version, then they are conjugate to each other. But if you use a higher block representation, you are basically enlarging the matrix by adding more zeros as eigenvalues. That's basically why here you have a power t to the power negative d. It's just to handle these issues of rescaling of the SFTs. So just think of this as you find a presentation, then you have a characteristic polynomial. And then we have the zeta function. So zeta function, it is defined by the exponential of the sum over exponential of this series, and the coefficient of each of the term Tn is Pn over n. This Pn is the periodic point of length n in periodic point of period n in the SFT x of w. And so basically, the zeta functions is think of this as encode the information of the number of periodic points of length n of different lengths into this polynomials, and then you take the exponential of it. That's what zeta function is. And it turns out that your zeta function is closely related with the characteristic polynomial in the sense of this. So zeta function is always 1 over a factor t to some power times the characteristic polynomial, but you replace the variable t by 1 over t. This is a well-known result in symbolic dynamics. You can calculate zeta function from the characteristic polynomial. And indeed, also, so the other direction is also true. You can, if you are given a zeta function, you can also calculate the characteristic polynomial from it. And another quantity we care about is the number of allowed words. Well, as it suggested, so we just check all the words of length n, which is allowed. Allowed basically means it does not contain the forbidden word w, and we use this b sub n to denote that set, and put kinetic to mean the number of those words. And finally, maybe another important quantity is the topological entropy, as I mentioned before. So they are just the growth rate of periodic points. Well, that turns out to be the same as the exponential growth rate of this set Bn. And in order to calculate that for SFTs, it's just indeed for Sophic also, they are just the log of the largest eigenvalue of the adjacency matrix. Okay, those are the quantities we care about. What's the relation between them? So here are some earlier results as we summarize all these results. Earlier results on the relation between these quantities. So it says that if U and V are two strings of length k over a finite alphabet, then the following are all equivalent. The first one says they have the same self-overlap set. The second says that they have the same correlation polynomial. Well, 1 and 2 are clearly equivalent because they have the same information. And the third one says they have the same zeta function. And the fourth one says for all n, the number of allowed words of length n of the two associated SFTs are the same. So if you count the allowed words, they give you the same thing. And the last one says they have the same entropy. So there are some of the directions I really want to point out here. Is maybe the most interesting one is look at 3 and 5. So 3 says they have the same zeta function. 5 says they have the same entropy. So in terms of the adjacency matrix of the two SFTs, well, this entropy basically corresponds to information on largest eigenvalues. So 5 is same as saying if you look at the adjacency matrix, they have the same largest eigenvalue. 3 zeta functions. So zeta functions is kind of bound over the characteristic polynomial. So this zeta function zeta function of a shift of finite type indeed captures information given by all the non-zero eigenvalues of the adjacency matrix. So usually this zeta function contains more information than the entropy. And the striking thing here is that 5 really implies 3. Which means that if you know two SFTs obtained by forbidding one word, if you look at two such SFTs, if their largest eigenvalue of the adjacency matrix are the same, then that tells you that the non-zero eigenvalues, the set of non-zero eigenvalues of them are also the same, together with the multiplicity of the eigenvalues. That's kind of the thing which makes this SFTs interesting, because usually we don't hope 5 will imply 3, but for these SFTs, they are. Okay, and also this 2 implies 3 is it gives the relation between characteristic polynomial and correlation polynomial. So this indeed is due to a very interesting result given by Douglas Lynch in it should be 89. And the formula says that the characteristic polynomial is given by this deterministic form, and from this formula you can tell that if you know the correlation polynomial, then you have the characteristic polynomial. That's why 2 implies 3. And just one more word on this formula. So this result you can consider it as a relation. So originally Douglas Lynch considered the problem of how the characteristic polynomial will change if you perturb SFT by further forbidding one more word. And his formula is intended to kind of handle that issue, tells you how the characteristic polynomial changes. And this one is kind of a special case of his general formula where think of the ambient shift you start with is a full shift, so that the characteristic polynomial of the full shift is just t minus q. So you think of this as the characteristic polynomial of the ambient shift. And then from that full shift, you further forbid the word w, then you have this correlation polynomial. And then this formula is really a formula which relates the characteristic polynomial of the new SFT and the characteristic polynomial of the old SFT. Okay, and this one in general can be another constant which it can be calculated from the adjacency matrix of the ambient shift. Okay. Yeah. So there's the relation between all those quantities, and similarly we have an inequality version of them, and mostly can be proved. I mean, it can be easily proved by using kind of contrapositive or whatever. So the inequality version of this, at least 3 quantities we're interested. So the first one, so again you have two words, and the following are equivalent. The first one says that the correlation polynomial evaluated at Q for U is larger than the correlation polynomial evaluated Q for V. Or so the value of correlation polynomial. So the one have more correlation compared to the other. And that's the same as saying if you compare the number of words of length n, then the number given by x of u is always larger than the number given by x of v. So you always have more allowed words for xu. And also that's the same as saying the entropy are the same. That's what this proposition says. So all 3 are equivalent. Okay, so If you still remember the question I raised at the beginning of the talk, then now we can answer that question. So let me remind you again, the question we had before is given two words, whether you can determine which one has larger entropy without any computation. Well, so the proposition here really gives us the answer. So A is equivalent to C that basically is saying that to determine which one has larger entropy, all you need to do is to look at the correlation polynomial evaluated at Q. So as an example, so this is the example we have at the beginning. U equals this, V equals that. Now the correlation polynomial of U is t to the power 4 plus 1. And this is t to the power 4. And evaluate at 2, then certainly the first one give you a larger value. Then from this proposition says that, well, x of U has larger entropy than x of V. Let's see if this is the same as your guess. Well, and just in case, I also calculate the largest eigenvalue of the corresponding adjacency matrices, and you can see that the value is really larger than the other one. So yeah, okay. But that's all from. I mean, all these things can be derived from earlier results, or just some simple generalization of the old results. Okay. Now let's turn to the main thing we care about. So symbolic dynamics always care about whether two SFTs are conjugates with each other. Or you can think of this thread as, well, since the length formula implies that if you have the same overlap set, that will give you the same entropy and also the same zeta function. Well, zeta function people usually consider as contains a lot of information of the SFT. So when they have the same zeta function, the next natural question to ask is whether the two SFTs are conjugate to each other. Or in other words, can you find a continuous shift commuting map which send one to the other? Okay, and this is basically the question we consider. And one quick observation is, well, SFTs can be represented by graphs, and one particular representation of them is a so-called follower set graphs. Whatever it is just think of it as a presentation of the SFT. Now, for both of them, you have the two presentations. Now, if these two presentations as graphs, they are isomorphic to each other, then certainly you have a conjugacy between the two SFTs. Well, this is immediate because the correspondence between, I mean, you have a one-to-one correspondence between the points in SFTs and directed passes on the graph. So when the graph is isomorphic, then certainly you have a conjugacy between those two SFTs. This is great. But, well, this is a good news. But on the other hand, we prove the following, which says that for two SFTs obtained by forbidding one pattern, then there's two presentations, GU and GV. They are only isomorphic if and only if there is a permutation on the alphabet Q which takes U to V. So this basically says that it is kind of rare that you can have two isomorphic presentations of those two SFTs. The only case is the difference between two words are given by flipping the bits. Or if you think of the alphabet as 2, then this permutation is really just flipping the bits. So this is bad news in the sense that if the two words are essentially different, there is no graph isomorphic conjugacy between those XU and XV. Okay. And then the next question we ask is, are there other conjugacies? Well, there's no, I mean, it is very rare to have these simple conjugacies given by graph isomorphisms, but are there other conjugacies? So we consider another type of conjugacy. So the idea of this other type of conjugacy is the so-called conjugacy given by replacement. And the idea is basically if you take a point, by point here we really mean by infinite sequence. If you take a bi-infinite sequence in the first SFT, and what we want to do is, well, it forbids U, but there may be some V's occurring in this bi-infinite sequence. So what we want to do is we want to replace all the appearances of V into U. And after the replacement, the resulting point, we want it to be in X of V. In other words, after you replace all the V's, then there's no new V's occurs in the point. Then you get a point in X of V. That's kind of how we want to construct the one-to-one correspondence between points of those two SFTs. And if this replacement gave a one-to-one correspondence in a good way, this good way basically means kind of continuous things or whatever, then you have a conjugacy between them. Okay, this is the idea of another conjugacy on top of our head. So here comes the next question: is when is this possible? And this is a fact which says that if both of the two words have trivial self-overlap, means that they don't. If you look at the overlap set, the only place they can overlap with itself is you directly put the word itself downward. If they have both trivial self-overlap and these two words have no cross-correlation, then you can then this replacement is possible, and it will give you a conjugacy between those two SFTs. The way to understand this is think of the replacement procedure. You have a v in the point x, then you replace it by u. But how to make sure that this gives you a log point in y? Then basically you don't want to have any new u's or new v's occurs after the replacement. That's kind of the thing you have to make sure to for this replacement to work. And and this exactly corresponds to the requirement that these two words have trivial self-overlap and no cross-correlation. Trivial self-overlap makes sure that the replacement is possible. If you have two overlaps of u here, you replace both of them, then it's then you can find two corresponding v's here. So that makes replacement possible. And no cross-correlation means that after you replace v by u, then there's no u occurring, so you don't have to do the replace again. So you can finish this game in infinite step. And for this type of conjugacy, it's really possible under these conditions. And this type of conjugacy, together with the conjugacy we considered before, which is a conjugacy given by graph homomorphisms, we consider those two as kind of the simple conjugacies, and altogether we call them swap conjugacies. After all the flipping of bits, you can consider it again as a change, as swapping one word with another. So we call this two conjugacies altogether to be the swap conjugacy. Okay. And let's take a closer look at this fact. So this requires, if you want to have a swap conjugacy here, according to this fact, it requires the two words have both trivial self-overlap and at the same time they have no cross-correlation. But if you have two words, it's very easy for them to have cross-correlation. So if you want to find words u and v such that both these two conditions holds, well, there are not that many pairs which satisfy both of these two conditions, because the no cross-correlation is really hard to satisfy. Okay, so again, this is not a very good type of conjugacy in the sense of you don't have much words which satisfy both of these two conditions. Then our next idea is we want to get rid of this no cross-correlation condition. And that turns out to be exactly the correct thing to look at. And here is our first main result, which says that if you have two words which only have trivial self-overlap, and we have no assumptions on the cross-correlation at all, then there always exists a conjugacy between them. And in particular, this conjugacy is built up from the trivial conjugacy, the swap conjugacy we defined before. This conjugacy is just given by a chain of swap conjugacies, and the length of chain is upper bounded by 5. So what's happening here is if you have no cross correlation, then you directly have a swap conjugacy between u and v. But if you don't have those no cross correlation assumption, then you can build a kind of you can build a chain of swap conjugacy to gradually to replace this u to something else, and then maybe something else to the second thing, and then the second thing to the third thing, and the third thing eventually to v. So that give you a chain of swap conjugacy. A composition of swap conjugacies certainly is also a conjugacy, and that's kind of what's happening here. And that's what this theorem says. 3 things I want to point out. Maybe start with the second thing, which is again the kind of interesting part of this theorem is we don't require any cross correlation on u and v. So this time you really have a relatively large pair of words. I mean, this theorem covers a kind of a relatively large class of words. And the first bullet here says that there are 4 exceptional cases So in the case q equals 2, then you have to rule out these 4 words. 1, 0 to the power k minus 1, 1 to the power k minus 1, 0, 0, 1 to the power k minus 1, and 0 k minus 1, k to the power k minus 1, and then 1. The reason to rule out these 4 cases is if the SFT is given by forbidding these 4 words, they are reducible. And for all other words, the corresponding SFTs are irreducible. So certainly there's no way for a reducible SFT to be conjugate to an irreducible SFT. So you have to rule out these 4 words. And indeed, for these 4 words, we know more. So the first one, if you look at the first one and the third one, the first one is the bit flip of the third one. So you can expect the SFTs given by the first one and the third one to be conjugate. And also similar for the second one and the last one. Well, but the first one and second one, the SFT is given by forbidding the first word and the SFT obtained by forbidding the second word. They are not conjugate. Because if you look at the graph, then one of them will have a source. Source means a vertex which you only have outgoing edges, and for the other you have a vertex which only have incoming edges. So the SFTs given by forbidding the first one and the second one are not conjugate to each other. So we fully understand the conjugacy properties of such SFTs. And the last thing I want to mention here is in this theorem, the trivial self-overlap set is very important in this result. So here's an example. If you have the length of the words equals 6, and you take the word u equals 100, v equals 110. Well, they both have the same self-overlap. Well, you can restart the word from the 4th bit for both of them. But their self-overlap set is not trivial. Remember, we trivial self-overlap set means the only number in the overlap set is k. You can only start the word from the very beginning, but not other places. But for this u and v, their self-overlap set is not trivial. So you can check that the only binary words which have this self-overlap set, you can restart here and here. There are only 4 words with this self-overlap set. 4 words of length 6 have this self-overlap set. And there's no way for you to build a conjugacy chain between them. So what we can say is, if the 2 words have non-trivial self-overlap, then the theorem may not be true. But this example only says that there's no swap conjugacy chain between them. There's still a chance that the 2 SFTs are conjugate to each other, and indeed that's a problem we were exploring, and we are also working on this to try to show whether these 2 SFTs are conjugate to each other. Conjugacy can be much more general than just swap conjugacy chains. Okay. And here's the idea of the proof. Well, it is not hard. Let me quickly explain this. So idea of the proof is, well, we for any given 2 words u and v, we want to build a swap conjugacy chain. And remember, swap conjugacy chain is given by replacing one word with the other. And this is possible if the 2 words have no self-overlap and no cross-correlation. So the idea is, from a u and a v, we try to find some kind of interpolations of the words so that any 2 adjacent words in this chain has no cross-correlation and has only trivial self-overlap. If you look at any 2 adjacent words here, they have no cross-correlation and no self-overlap. That's kind of the idea of how we want to prove the theorem. So for the class of words with trivial self-overlap, we first pick some kind of representatives. Think of them as so you think of the space of words with trivial self-overlap as a large set. Then you choose some representatives in the sets, and for each of the sets, you create some clusters. Where inside the clusters, there are some other words which have no cross-correlation with the centers of the clusters. And turns out that those clusters will almost cover the whole space. There are some exceptional cases, but that can be dealt with. That can be easily dealt with one by one. That's kind of the idea. Using the example to illustrate the idea is, if you if you have the word U and have word V like this, well, you have a trivial self-overlap you can check. We also have trivial self-overlap you can check. But clearly there are some cross-correlation between them. Say the last word of U is 0, the last letter of U is 0, the first letter of V is 0. So at least they will overlap in the last bit. So they don't have so they do have non-trivial cross-correlation. And then how do we build up the swap conjugacy chain? Well, U is this word. Then you first choose kind of a test word, and you can check that this word, the U, and the first word here, they have no cross correlation. And the word V here, you first flip it to have a word starting with 1 and ending with 0, and you have the second last word here. And also we choose another representative in the space, which looks like this. And you can check that this word has no cross correlation with the word here. Okay, and now for this word and this word, for the two representatives, there's a typical way to find another word which can connect both of them. So we find this word which has no cross correlation with both this one and this one, and eventually we build up a chain of words from U to V, where for each two adjacent word in this chain, they have no cross correlation, and that's how we build up the conjugacy chain between them. Okay. So having proved this theorem, the next question we consider is kind of can we generalize this result to the case when we start with some more general SFTs. So previously we considered the case where we forbid one word from a full shift. So think of the ambient shift as a full shift, and then you consider forbidding one word from that ambient shift. Now, what if the ambient shift is not a full shift, it's more general? So the first thing to try is always a golden mean shift. That's the easiest one. Well, I should say easiest. I mean, that's always the first thing people consider. So that's a problem we consider now. So what if you start with a golden mean shift and you further forbid a word U or forbid a word V from the golden mean shift? You get the two corresponding SFTs. Can we say something about them? Well, there are some expectations. So first of all, Lind's formula. Remember Lind's formula, as I mentioned before, it gives you a relation between the correlation polynomial and the characteristic polynomial of the SFT obtained by further forbidding that word. And this formula has a general form where the formula is just given by this. From here you can see that it tells you that the characteristic polynomial of the new SFT is related to the characteristic polynomial of the old SFT and also the correlation polynomial of the word you further forbidden. So from this one, you know that if two words have the same cross correlation, no matter whether you start with a full shift or not, then you can always have the same characteristic polynomial. That's what this second bullet is saying. So if they have the same overlap set, well, the second bullet here is kind of the same extender set. That's kind of technical condition you always need. When you want to extend the word to the left and to the right, you want the extension to be the same for both of the two words. So if they have from this formula, if you have the same overlap set, then the characteristic polynomial of the corresponding two SFTs by forbidding U or V from the golden mean shift, which we represent by this and this. They always have the same characteristic polynomial and certainly have the same zeta function, because zeta function and polynomial, one of them determines the other. Okay, the same zeta function. So again, same zeta function. The next question to ask is whether they are conjugate to each other. And it turns out that they are. So, and that's what our next theorem says. Says that, except for some exceptional cases, this is similar to the ambient full shift case. These four words will give you a reducible SFT. And other than this four exceptional cases, then there is always a swap conjugacy chain between the two SFTs obtained by forbidding U or forbidding V from the golden mean shift. So we can really generalize our previous result to the case when the ambient shift is a golden mean shift. Okay, And the idea of the proof is similar. So you choose some test words, think of them as centers of clusters. And the only difference is this time your center of clusters, those words has to be of a different form, because after all, these words are not allowed in the golden mean shift. You may have 2 ones at the beginning. Okay. Now those two theorems I introduced before kind of our main theorems in one dimension. Now let's move to higher dimension. We don't, as I said, we don't have that much result. We don't have any conjugacy result in this higher dimension case, but we do have some weaker results. So before introducing those results, so again, we must have a corresponding definition of the overlaps of patterns in higher dimension. So given so if you consider a ZD and you consider a finite set S in ZD, and there's a pattern, you consider a pattern U supported on this S, then you can define the overlap set of 2 patterns in higher dimension as the set of, in this time, instead of the numbers, we consider kind of the vectors. It consists of set of vectors, or the sets if you want, where if you translate the pattern S by this vector, then the 2 patterns S and S plus I, U and U plus I, they agree on, they have the same pattern on the intersection of their supports. So it's the same idea as in one dimension. You translate the pattern, you see whether they agree on the intersection. And you just take the set to be the collection of all those sets, all those translations. And having those overlap sets, then we have to introduce another. It turns out that the relation between the overlap set and the other quantities in symbolic dynamics is not as simple as in the one-dimensional case. So we have to introduce another notation here, which is called mutually replaceability. So it basically says that if you start with an ambient shift X and you take 2 words U and V, and we say that U is replaceable by V if, think of, again, you take a point in X and you may have some occurrences of U, and whenever you have occurrence of U, you replace it by V. If this replacement is possible, and it after the replacement, it gave you a allowed configuration in X, basically means that there's no U occur, and also the point obtained after the replacement is also in the ambient SFT X. Then we say that U is replaceable by V. And similarly, you replace the row of U and V. You have when you have a definition of when V is replaceable by U. And U and V are mutually replaceable means that if U is replaceable by V and V is replaceable by U. That basically means you can safely replace one by the other, and which result in allowed point in the ambient shift space. And this sounds similar to something we considered before, but I really want to let you know that there are some subtlety here for higher dimensional one-dimensional case. So when X is a full shift, then U is replaceable by V if and only if the overlap set of U is a subset of the overlap set of V. So if U can overlap in these positions, V certainly can also be. V can certainly be overlapped with itself at these positions. Then if you replace U with V, there's no problem. There's no mismatch after the replacement. But that's only the case for the full shift. But if X is not the full shift, then things become kind of subtle. So here is an example. So though this is in one-dimensional case, but the point is that the ambient shift is not a full shift case. The ambient shift is not a full shift. So if your ambient shift is given by forbidding this 2 words 0, 1, 0, 1, 1, 0, 1, 0, and you consider 2 words U equals 101 and V equals 122, then it's clear that the overlap set of U is at the first place and the last place, but the overlap of V, self-overlap of V, only have trivial self-overlap. So certainly the overlap set of U is not in the overlap set of V. But you can check in this case, U is still replaceable by V. That's because, so in the full shift case, U is not replaceable by V. That's basically because you can have a word like 10101, which are kind of two overlap occurrence of U. In the full shift case, if we want to replace these two U's by V's, it's not possible because you cannot have a 122 and 122 where the last bit is where the 1 and 2 coincide. So in the full shift case, you cannot replace U by V. But in this case, if the ambient shift is a word forbidding 0101 1010, then that thing will not happen because after all, the long word 10101 is not allowed in the ambient shift. So you will never see two overlap of non-trivial overlaps of two U's. And that's what makes this different. So in the one-dimensional case, remember, we always consider the case when the ambient shift is a full shift. And in that case, that's the same as we have this trivial relation between replaceability and the overlap set. And indeed, in that case, the mature replaceability is the same as the two words have the same overlap set. But when your ambient shift is not the full shift, then that's not the case at all. So our assumption will be so our assumption has to be changed. And so here is kind of our results. So well, this is just a notation where you use this to denote the set of allowed patterns on S. And think of this as a generalization of BNs in one dimension. When you want to talk about allowed words, you have to fix length in one dimension, and in the entire dimension, you have to fix a kind of support of the words. That's what this S is. And this theorem basically says if you start with an ambient SFT X of F, and you let the two words U and V be in the ambient shift first of all, and then they have to be replaceable. They are materially replaceable. Then we have a bijection between the number of allowed between the set of allowed patterns on S and the set of allowed patterns. The set of allowed patterns on S in the new SFT by further forbidding U from X of F, and the set of allowed patterns on S in the SFT obtained by further forbidding V from X of F. So so this is kind of an analog of the one-dimensional case in the sense that if you consider this set as the number of allowed words, then it says that if the two words are mutually replaceable, then you have a bijection between the set of the set of allowed words. And the idea is, I won't go into the proof of the theorem, but the idea is simple. Just use the definition of mutual replaceability and include an equivalent principle. And I want to point out here that we don't know how to prove the converse. Well, the converse basically says if you have a bijection between the number of allowed words, or I should say number of allowed patterns, then the two words are mutually replaceable. We don't know how to prove that direction. But to compare this one with the previous easy case where we are in the 1D full shift case. Well, in the 1D full shift case, we really can prove we really have the converse. Because in the 1D case, then if you assume there is a bijection between the set of allowed patterns, that basically means you have a same number of allowed words of length n. And remember, we have 5 equivalent things. The overlap set, same overlap set means the same entropy, same zeta function, etc. So if you have the same number of allowed words, then certainly you know that the two words have the same overlap set. And from the previous page here, the same overlap set basically means the two words are mutually replaceable. So in the 1D shift case, we do have the converse, but in higher dimension, we don't. And there are several reasons for this. One of them is the overlap set turns out to be more complicated in higher dimension. So in one dimension, there's a paper by Guibas and Odlyzko called Strings of Periods of Strings or something like that. So it's a very early paper which characterizes the set of overlaps of a word. Basically, in one dimension, they gave two conditions called forward propagation and backward propagation, which characterizes when a set can be the overlap set of a string in one dimension. But in higher dimension, we don't have this characterization. And in my opinion, in higher dimension, we need more conditions in order to give these characterizations. Only the forward and backward propagation is not enough. That's kind of why we don't have the converse in this higher dimension, and that also illustrates why things become more complicated in higher dimension. And at last, so we have in symbolic dynamics always care about, well, you can't talk about conjugacies, and we may consider kind of the correspondence between the periodic points, because periodic points is usually the things we care about. And our last result is basically says that, well, if similar assumptions as before, if the two words U and V are materially replaceable, then you have a bijection between the set of periodic points. And here we need different notations because, well, your fundamental domain of the subgroup, given by the subgroup, can be finite or infinite. And when the fundamental domain is finite, then you can count the number of periodic points. Otherwise, you have to use kind of asymptotics to define to compare the number of periodic points. So that's what's happening here. So as the first bullet says, so if U and V are materially replaceable, and if the fundamental domain is finite, so that you can count the periodic points, then you have a bijection between those 2 points, which necessarily gives you that you have the same number of periodic points. But if the fundamental domain is finite, where you have infinite many periodic points, then you can't count them, but their asymptotic rate, which basically give you topological entropy, then their asymptotic rate are indeed the same. That's kind of what's happening here. And that's the last thing I want to introduce. And I think that's everything I want to talk about here. And thank you for attention.
Thank you very much. Thank you. Okay, so are there any questions also online? I wanted to ask you a couple of things. One is that first, in your definition of this kind of self-overlap in higher dimensions,
yes,
you allow the domain of the pattern to be not contiguous, right?
Yes, so, that's right. That's right.
So have you considered doing something like that in the one-dimensional case? Is it interesting?
Yeah, that's a good question. So indeed, in that one-dimensional case, we do have some results, and that's indeed not the result due to us. That's due to Guibas and Odlyzko. Let me go back to the point where I mentioned the equivalence between those relations. Like here. So in this proposition here, we assume that these two words they support adjusted intervals, and in that case, we have all these 5 things are equivalent. And indeed, eventually, we also prove that they have the same. Indeed, we eventually prove that the 2 SFTs are conjugate to each other. Okay, so in the case where the 2 words are not consecutive, and you can think of that case as forbidding instead of 1 word, but forbidding 2 words.
Okay.
Okay, and Guibas and Odlyzko prove some result in that case. That is, let's say you forbid 2 words. So you start with a full shift. If you forbid the 2 words, let's say U1, U2, and you forbid another word V1, V2. And in that case, in order to get this equal entropy or equal count of numbers, then you need now your assumption should be the overlap of U1 is the same as the self-overlap of V1. The overlap of V2 is the same as overlap of U2. And the cross-correlation between the first 2 words is the same as the cross-correlation between the 2 words in the second set. Or in other words, now you have 2 sets of words, so all their correlations you have to have a 1-to-1 correspondence between them. And in that case, you can have similar results here, like same number of words, same entropy, I believe, and similar things. But we don't know whether those SFTs will be conjugate to each other or not. For the conjugacy result, for now, we can only prove for words whose support is interval. It's a single interval.
Okay.
Thank you.
Thank you. And another thing, when you talk about these swap conjugacies, you say you define them as you replace the appearance of U in V, right? But these swap conjugacies, does it swap? It means if you will have this acting in the full I mean, sorry, let me think what I want to say. What I want to say is this conjugacy, the only thing that it does is just swapping U in V, or it might be doing other stuff in the chain. When the conjugacy is reading, let's say, a bi-infinite sequence in the subsheet, is the only action that is doing in this sequence is replacing one word by the other one, or is it doing other movements, or other replacements?
So there's no movement. Oh, you only replace one word by the other, but you're just following the chain. You're changing one word with another at the time, and then you move to the another pair of the words.
Okay,
but by replacement, we really mean replace all the occurrence.
Replace all the occurrences of this word by the other, and somehow this defines something bijective, right? At the end,
Yes.
that's the important thing.
I mean, there should be no movement because if you look at this chain of conjugacies, if you look at, for example, these chains, you take any two adjacent words, they have no cross correlation. So you're not kind of translating things to the left or to the right. So all you're doing there, if you focus on these two words, two adjacent words, that's just a replacement.
Okay. Great. Okay, thank you very much again then. If there's no
thank you for the next question. Yeah.
Sorry?
Thanks for your next question.
Thank you very much. Thank you for your answer. And thank you everyone for coming. Muchas gracias a todos.
Thank you.
Okay, so thank you. We'll see. We'll keep in touch. Thank you very much for your talk.
Sure. Keep in touch.
Thank you. Bye.
Have a good day. See you.